today we have optimization. So optimization, and for calculus, I say everything's a fancy word. So optimization is a fancy word for finding maximums and minimums of an application. So if we want to maximize something or minimize something, we say we're going to optimize it. So if you ever see the word optimize, that just means find a maximum, find a minimum. And we know how to do that. To find a max or min, we find the first derivative, we set it equal to 0, and we solve for x. And that'll help us find whether if it's a max or min. So when you optimize, again, it doesn't matter. As long as it says optimize, you're either finding a max or a min. So it's the same process. Okay. So to get us used to optimization, we're going to work the first two examples, which are all about optimizing a rectangle. And then that'll lead us into an actual word problem, a business word problem. So why do students need to know about optimizing rectangles? Who knows? Maybe your business will be in building fences or houses or something, right? Okay. So the first example, find the dimensions of a rectangle with an area of 200 square feet that has the minimum perimeter. So in this example, it's already telling us what to optimize. This is telling us to minimize the perimeter. Okay, so what we're gonna do first is I'm gonna draw a diagram. Here's my rectangle. I'll label the width X and the height Y, or length X, width Y, whichever. And we need to know two formulas for a rectangle. One is going to be the area of a rectangle. The area of a rectangle is given by length times width, or in our case, X times Y. And then the other formula we need is the perimeter formula. So perimeter is given by 2 times the width plus 2 times the length. Or I'm probably saying it backwards. Either way, 2 times length plus 2 times width. Okay. And from this problem, our goal is to minimize this function. We're going to minimize it. Okay, which means we're going to take the derivative. But if we take the derivative now, we're going to come across a variable that we don't need. And I'll show you that. Let's say we wanted to already take the derivative of the perimeter equation. And we take it with respect to x, which means I'd get p prime equal to 2 plus 2 y prime. Now, y prime is the variable that we don't need, because y prime would actually change this problem into a related rates problem, and that's what we don't want. Y prime would mean that the rectangle is constantly changing its width. We would be given that, hey, y prime, the rectangle is changing at 2 feet per second, which this is not a related rates problem. This is an optimization problem. So we want to avoid variables we don't need. So that's why we don't take the derivative right away. So with optimization problems, we're always going to have to make a substitution. So our goal is to get rid of this y by making a substitution. So that's what we're going to call step 1. Or I'll call it, yeah, I'll say step 1. Make a substitution. Make a sub. All right. So to make the substitution, we're going to use the information that they've given us. So in the problem, they said we have a rectangle with an area of 200 square feet. So this means we're going to use that area equation, A equals X times Y, plug in 200 for the area. And the next thing we're going to do is solve this equation for Y. So all I have to do to solve for Y is divide by X, and I'll get 200 over X is equal to Y. Here is my sub. So what we're going to do is take this new value of y and plug it into the perimeter equation for y. So we'll make that a step. We're going to say 2 plug y into the perimeter equation. Okay, so here we have p equals 2x plus 2y. And now we're going to plug in the equation for y, which is now given as 200 over x. Okay, and then simplify, and we get 2x plus 400 over x. And if we're going to take the derivative of this, we want to make it look a little neater. So this is going to be 2x plus 400x to the negative 1. And what we have done is put the perimeter equation all in terms of one variable, which means if we take the derivative now, we are not going to get that pesky y prime, because in this type of problem, y prime means nothing to us. So we want to avoid that mistake. Okay, any questions before we take the derivative? Probably no questions yet, right? Find p prime and set p prime equal to 0. Okay, so what we're going to do is say d over dx of the whole equation, p equals 2x plus 400x to the negative 1. So we're going to take the derivative with respect to x of this whole equation. And we're going to get p prime equal to 2 minus 400x to the negative 2. There's our derivative. And now set it equal to 0 and solve for x. 2 minus 400x to the negative 2 equals 0. I'm going to add that 400 over. That 400x to the negative 2, we add it to the right side. And then I'm going to rewrite 400x to the negative 2. I'm going to take that and flip it to the denominator as 400 over x squared. And since we're solving for x, we need to get rid of it out of the denominator. So I'm just going to multiply it to the left side, which will give us 2x squared equal to 400. And then divide by 2. X squared equals 200. Square root both sides. And x is going to equal, let me see, square root 200, 10 square root 2. So you get plus or minus 10 square root of 2, or 14.14 feet. Now we only keep the positive value because we're dealing with length. And remember, length can only be positive. Okay. So in this question, all it wants to know is what are the dimensions that would minimize this perimeter. It just wants the dimensions. So we found out now that to minimize this perimeter, x has to be 14.14 feet, which means to finish this off, all we have to do is solve for y, which means we're going to take x and plug it into that substitution we made, that substitution equation we made for y. So that's going to be our fourth step. 4. Plug x into y. So this means you're going to get y equals 200 over x, which gives me 200 over 14.14, which gives me, hey, look at that. Y is also 14.14 feet. So this means that if you optimize a rectangle, you're going to get what shape?
A rectangle.
A square.
A square, because the sides are the same size, right? So my dimensions would be 14.14 feet by 14.14 feet. There you go. And that's how optimization works. So we're going to have to replace a variable, one that we don't need. So we make a substitution for y. We put the equation all in terms of x, take the derivative, set it equal to 0, solve for x, and then plug x in to find the other components. Any questions on this one before moving on?
Will it always be a square, or is that just in this equation or this one it happened to be?
I think it depends on the problem, but I think majority of the time, if you ever optimize a rectangle, it should become a square. Unless we're talking about like farmland and stuff, rectangles work better out there. But if you think about it, your room's a square, a classroom's a square, a business is a square. Squares are everything.
What is it but other than two triangles?
Exactly. Triangles work too. Triangles make bridges. All right. Let's try another rectangle one. So find the dimensions of a rectangle with a perimeter of 148 feet that has the maximum area. So again, I'm going to draw my rectangle just to have it, label width or length x with y. And we know that area is x times y, and perimeter again is 2x plus 2y. And now this problem wants us to maximize the area. So find the dimensions of a rectangle that has the maximum area. So we need to maximize this equation. But again, what variable gets in the way?
The y.
The y. So again, number one, we make a sub. Using the information given, they tell us that this rectangle has a perimeter of 148 feet. So we're going to take 148 and set it equal to the perimeter equation. We're going to solve this equation for y, which means move that 2x over. 148 minus 2x equals 2y. And then divide everything by 2. And we will get 74 minus x equal to y. Here is our sub, which we're going to plug in for that y into the area. So 2. Plug y into area. Okay. So A equals x times my new equation for y, my substitution for y, which is 74 minus x. Distribute the x, and we get area is 74x minus x squared. This is my area equation, all in terms of one variable, all in terms of x, which means we are ready to move on to the derivative. So 3. Find a prime and set a prime equal to 0. So take the derivative of the above, a prime, you're going to get 74 minus 2x. Set it equal to 0, and 74 minus 2x equals 0. Add the 2x over and divide by 2. We get that x is equal to 37 feet. So that means in order to maximize the area of this rectangle, x, the length of x needs to be 37 feet. So all we have to find is y by plugging x back into our substitution. So 4. Plug x into y. And we get 74 minus 37 equal to y. And 37 feet is equal to y. Where again, in order to maximize this area, the length needs to be 37 feet, the width needs to be 37 feet, and again, we have a what?
Square.
A square. It's because squares are cool, right? What weren't you allowed to hang out in high school? You were not allowed to hang out in the hallways, which were rectangle. Oh, logic, right?
Or where all the squares were.
Here you go. Okay, cool. So that's optimization on a rectangle. And again, I guess we're more looking at the process here. We're going to be given components. We're going to make a substitution. We're going to put it all in terms of one variable, find the derivative, find x, and then plug it into whatever we need. Okay, any questions on that before moving on? Ooh. Not bad, not bad. Okay. Now we get into an actual word problem. So 3, an office supply company sells X permanent markers per year. The yearly price demand equation for these markers is P equals 10 minus 0.001X. The total annual cost of manufacturing X permanent markers for the supply company is given by C of X equals 5,000 plus 2X. A, what price should the company charge for the markers, and how many markers should be produced to maximize the yearly revenue? And what is the maximum yearly revenue? So for A, our job is to maximize the revenue. We're not given a revenue function, but we know how to create a revenue function. If you remember from, what was that class? 1324, so long ago, a revenue function is given by the amount of items X times P, the price. Well, in this problem, where are we given an equation for P?
Yes.
Yes. So we're going to substitute that in for P. Hey, it's a substitution. That's what we've been doing today. So you're going to get X times 10 minus 0.001X distribute the x, and you get 10x minus 0.001x squared. Here is our revenue function. And now, since we know the revenue function, and since we made a substitution that put this function all in terms of x, we are now going to take the derivative and solve for x. So we're going to say r prime of x, that's our next step. And we take the derivative of the revenue function we just found. And we're going to get 10 minus 0.002x. After you do that, you set the derivative equal to 0. And solve for x. I'll add the 0.002 to the right side, and then I'll divide by 0.002. All right, and 10,000 over 0.002, assuming that that is 5,000. All right, so we have our first answer. We get 5,000 equal to x. Well, remember in this problem, we are creating markers. So it's asking us how many markers should we produce in order to maximize revenue. So this is the first answer. We need to produce 5,000 markers. Okay. All right, next. It says in step A, we're still in step A. What price should the company charge for the markers? How many should we make? We found out we should make 5,000. And then it says, what is the maximum yearly revenue? So all we're going to do now is take this answer of 5,000. We're going to plug it into the revenue function, just the regular revenue function, because that'll give us the maximum yearly revenue. And then we're going to plug it into the price equation to tell us the price we should sell the markers at. So we're going to plug them into both of those equations. All right, so let me zoom in a bit. 5,000 is the number. Revenue function's there. All right, and I'll call this max revenue, which means we're going to say R of 5,000, and we'll get 10 times 5,000 minus 0.001 times 5,000 squared. And let me just punch those in my calculator real fast. 10 times 5,000 minus 0.001 times 5,000 squared. And if we produce 5,000 markers, our max revenue is going to be $25,000. So that's maximum revenue. And now, price. We take 5,000 and plug it into that price equation above. P equals 10 minus 0.001 times 5,000. And in order to make $25,000 in revenue, we need to sell these markers. I'm assuming that's $5 for $5 per marker. Let me double check though. $5 per marker. Okay. There we go. Any questions on A? So I think in your homework, you'll create the revenue function, you'll take the derivative, you'll find the number of markers to make, and then you'll take that number, plug it back into the revenue function you found, and plug it into that price. I think that's all it wants. Okay. And then B, what price should the company charge for the markers? How many markers should we make to maximize the annual profit? What is the maximum annual profit? So now our job is to maximize profit, which means we need to create a profit equation. And remember that profit,
Revenue minus cost.
good. Profit is given by revenue minus cost. So we're going to plug in the revenue function we created above, which was 10x minus 0.001x squared. And subtract the cost function they gave us in the problem. 5,000 plus 2x in the beginning paragraph. And whenever you plug in that cost function, make sure to keep it in parentheses. This negative has to distribute to both terms. So we get 10x minus 0.001x squared minus 5,000 minus 2x. Okay. I'll combine like terms and I'm going to write the highest power first. So I'm going to have negative 0.001 x squared. I can combine my x's. That'll give me positive 8x minus 5,000. There's our profit equation. And now since we found profit, we can take the derivative, solve for x, and plug it into where we need to. Okay. So P prime of x is going to give me negative 0.002x plus 8. There's the derivative of the profit function. And then set it equal to 0. So negative 0.002x plus 8 equal to 0. Solve for x. This time, I'll move the 8 over. Equal to negative 8. And then divide by negative 0.002, negative 0.002. And then 8 over 0.002 gives me positive 4,000. Oops. So x equals 4,000 markers. This is how many we need to produce to get the maximum profit. Okay, and now, since we know the number we need to produce, we're going to take that number and plug it into the profit function, and then plug it in to the price equation that they gave us in the very beginning. So let's start with profit. 4,000 markers. So P of 5,000 going to be plugged in to this profit equation. Not 5,000,
I was gonna say 4,000, right?
4,000. Keep you on your toes. There you go. Minus 5,000. Okay, plug that in. Let's see, negative 0.001 times 4,000 squared plus 8 times 4,000 minus 5,000. I get $11,000. So this is max profit. Okay. And then last is price. P equals, what was the equation? 10 minus 0.01. Okay. 10 minus 0.01 times 4,000. And that should give us $6. There it is. So in order to make a max profit of 11 grand, we now need to make 4,000 markers and charge $6 per marker. Now remember that profit is take-home money. Revenue is the amount of money you made, but you're going to have to subtract the cost to get you the profit. So since we added a cost function on the second step in B, we saw that we don't have $25,000 anymore. We had to subtract 14,000, which is in cost, to get to that 11,000, which means we have to produce less markers because maybe the cost is killing us. We produce less markers and we sell them for more, $6 per marker. Now, I don't know what marker costs $6, but hey, maybe a pack of markers, right? But that is optimization part 1. We get part 2, I call it part 2 and 3. We'll do that on Thursday. But any questions on these notes?
Oh, that was pretty cool. All the stuff we've been using, put it all together.
Right?